So this is the basics or fundamentals of protection. And we can have we'll have a three-phase system. A phase, B phase, and C phase. And we can have connections there. Okay, so this is a three-line drawing. And we can represent that as just one line. Okay. Then coming off of that one line, we can have just one connection. Again, that's going to be one line going to a 52. Okay. And let's say we've got 2,000 amps going down that line. We could have our PT here, our CT here, all right? And that will go into what? Our nice relay. So the relay can send a trip signal back to the circuit breaker. Okay. So this could be 138 kV. We step that down with the PT or the VT. And at 2,000 amps, we could have a 2,000 to 5 CT. And so we'd only have 5 amps. Okay. And based on the settings of our relay, we could tell the breaker to trip. Okay. If the current gets too high, if the voltage gets too high, depending upon what we're looking at with the relay, we could do that. Okay. So this would be our one line diagram. We could also have our logic diagram. Can you see this color okay? Oh, okay. I won't use that one. They gave me too many choices here. There we go. Now, usually the logic diagrams are going to be like this, where we have plus 125 volts DC, and oh, I said that was plus, and this is going to be minus 125 volts DC. So what are we going to have there? We're going to have a coil called CS. We're going to have the relay. We'll have the 52, oh, that would be the B. Normally open 52A. And the 52T, like that. Okay. Do you want me to redraw that? I started to show it as a normally closed connection, but it would be normally open. A 52A is closed when the breaker is closed. So does that make sense to everybody? We'd show it as a normally open. But when the circuit breaker was closed, that would be closed. All right? So if the circuit breaker is closed, okay. So when the relay senses a fault, what do you think is going to happen? No. The relay guy is going to close, right? Okay. Okay, so the trip coil causes the circuit breaker to open. Okay, when it begins to open, that's the relay is going to open again, right? When we start to open the circuit breaker, the relay would no longer see a fault. So what's going to happen to that relay contacts? Now this would be a problem, right? Because the thing that's energizing the trip coil, this relay, is starting to open. Okay. 52A will not open until it's completely closed. Okay, so 52A is going to be closed, but if this relay opens up, 52T Okay. Does that make sense to everybody? We've got this coil, which is a coil wire, so we'll always have current through there as long as the path is intact. So the relay has to be closed, the 52A has to be closed, and 52, if those two relays are closed, 52T is going to be energized. Okay? Relay contacts are going to open as soon as the fault is cleared. So as soon as the breaker starts to open, these contacts right here are going to open. So what can we do to prevent that? Okay? We'll put a set of contacts in parallel with the relay contact. Okay? Nowadays, if you've got a microprocessor-based one, you can handle all this in microprocessor. Some people still like to do it, but so if you had electromechanical relay, and the reason for tripping would be an overcurrent, as soon as that circuit breaker starts to open, that overcurrent is going to decrease, right? And it might be not enough to trip the relay anymore. So we put this CS in parallel with the relay so that when this CS coil is energized, this is closed. And the circuit would remain true until 52A opens up. Is that making sense? Is everyone okay with that? These two guys close. This path is closed. We got current going from the 120 volt positive to the 120 volt negative. So we got current going through here. It's going to energize the 52T coil, which causes the circuit breaker to open up. But the instant that it starts to open, there's going to be an arc, but that arc is going to have high resistance. So the current will go down, right? And that might not be enough to keep this thing closed. So to keep it closed for the whole process, we put this coil in parallel with the relay coil. So the only thing that will cause this circuit to open once the relay closes is 52A. Okay? Any questions on how this relay logic works? Like I said, in microprocessor-based relays, you can keep a time on there that it will stay high. So once it says to trip, it'll stay in the trip position for a second, which will give the circuit breaker plenty of time to open up. That's 60 cycles, right? So the breaker should be open up by then. Okay. So we don't need this. If we've got the old-fashioned electromechanical, we definitely need this because, again, the electromechanical is limited. It has to have that signal, that high current signal, in order to trip the breaker. And once it loses that high current signal, it's not going to be sending that trip signal on anymore. I can do this here. So our relay scheme is only dealing with when bad things happen. It doesn't prevent the bad things from happening. Okay, so we're not doing prevention. We're looking at the system, and when there's a fault, we're doing something set to try to minimize the effect of that fault. Okay, but we're not getting rid of faults. Okay, we can do other things to try to protect from lightning, other things to protect from fallen tree branches, and other things to protect from operator error. Okay, so the things we want reliability. We want selectivity. We want speed. We want simplicity. Okay. Okay. And we have to look at the cost. Okay. So if you got something that's really good on those first four items, but it's not very economical, it's never going to be put in place. Okay. Does that make sense? You've got a system that costs $1 million. All right. So do all these things for you. The customer is only worth a few $100,000 in yearly energy charges. There's no way you're going to use that control system, that protection system. So let's look at each one of these. So the thing that works correctly is your dependability. Oh man. Okay. So it works correctly. We can test that. We can put current in there into the relay and make sure it works. And that's dependability. Security is it will not work incorrectly. That's very difficult to check. Okay. You've got an infinite number of possibilities with these relays. And to completely check the security, you'd have to run through all those scenarios. Does that make sense? So it works correctly. You've got the trip point set to 20 amps. That's on the 5 amp CT side, 5 amp side of the CT. And you can test that, and it works correctly, so you're good to go, right? That's dependability. But are you sure, given a certain voltage and current, that it won't work, it won't trip for the wrong settings? Okay. So you could check it, let's say you wanted it to trip at 20 amps. So you put 20 amps through the relay, it trips. It's dependable. You put 17 amps through the relay and it trips. It's not very secure. Does that make sense? So there's two parts of reliability, dependability and security. Dependability is easy to check. Security is very difficult to check. Selectivity. Okay, so reliability is dependability and security. Selectivity is you're only going to open that part of the system where the fault is, okay? You don't want the entire town of Ishpeming to go black if there's just one transformer on a street that's shorted, right? That would not be a good idea. So everyone understands selectivity. Okay. Speed. There we go. Speed. Okay, so speed is the time that it takes for you to recognize that there's a problem, send that trip signal, and open the breaker.
So like, they would have to recognize it, send it all the way back to the relay.
That you have to be able to recognize it, okay, I'm supposed to operate, send the signal to the circuit breaker, and have the circuit breaker open.
Okay, will a relay do that all by, by itself, or?
Well, the first two things, the relay does. The third thing is up to the circuit breaker.
Yeah, but like, will the relay control the circuit breaker too? Or like, you know what I mean? Like, will it send a signal to the circuit breaker to?
Yeah, it will send the signal,
Like,
but
you wouldn't have to have a guy there that.
no. So it's sitting there and it's looking at the voltages and currents, and they're off from what they should be. Is that something that I should open the circuit breaker for? It has to determine that, send the signal out to the circuit breaker, and then the circuit breaker has to open.
Is that usually pretty fast then?
What?
Is that usually pretty quick?
Yeah, well, so fast would be 1 to 3 cycles. Okay. So 1 cycle is 16.67 milliseconds. To 3 cycles is 50 milliseconds. So 5 cycles would be 83.3 milliseconds. Okay. Is that making sense? Okay. Okay. So that's speed. Simplicity. We're talking about fewer elements and a standard configuration. Okay. So if you've got a relay that depends upon all kinds of things, that you're sensing the phase angle difference, you're looking at the travel time of the line, all kinds of goofy things. That's not a simple control circuit, a simple relay circuit, right? So you want to limit the number of parts, and then most utilities want a standard configuration. Why would you like a standard configuration? Relay techs are going to all the substations, right? If each substation has a different way of doing bus protection or a different way of doing line protection, it's going to be very difficult to be switching gears all the time. So utilities standardize on this is UPCO's way of controlling and protecting the line. This is UPCO's way of doing a bus differential scheme, okay? American Electric Power might have a different scheme, okay? But they'll have standard. The other thing American Electric Power has that a lot of other companies don't have is they always have a backup system that's made from a different manufacturer. So a lot of people use Schweitzer, but American Electric Power, which is one of the biggest power companies in the United States, likes to use Schweitzer and then either GE or ABB relays as backup, okay? So they always have two sources for their relays. And if there's a problem with somebody's algorithms that they're using to detect a fault, hopefully the other manufacturer didn't copy the first manufacturer's algorithm. So it should, hopefully the backup one will be able to sense the fault. Does that make sense? Okay. And then lowest cost. That's the economics of it. So we've got reliability, which is broken into two parts. Selectivity, which is make sure you only open up one part of the grid, not the entire grid. Speed, we're talking about fast being 1 to 3 cycles, normal being 5 cycles. Simplicity, and then cost. So those are the 5 things. Is it 5? Yeah, those are the 5 things. Okay. I put always in quotation marks. Unless there's outside factors. Okay? The companies are always going to go with the lowest price. Initially with Schweitzer relays, the other manufacturers were saying, oh, they don't work, they don't work, they don't work. So even though Schweitzer had a less expensive relay, the companies weren't going with that. That was back in the 80s. Nowadays, nobody mistrusts Schweitzer. They're considered the gold standard. Okay? I guess AEP somewhat mistrusts Schweitzer because they want to have backup be from a different manufacturer. Okay? They don't trust anybody. Does that make sense? Okay, so that's the beginning of looking at these relays.